Today we're starting our topic on binomial theorem. So we're going to be looking at binomial expansions, which means we're going to be expanding things like this. We're going to have something like 1 minus x in the bracket, and it's going to have a power. Now we are used to expanding normal brackets or powers of 2. We can do powers of 3 with a little bit of work, but we also want to learn how to expand things with much higher powers as well. And I'll be showing you some strategies to use for that. A binomial, the word binomial means that it comes from a polynomial with 2 terms. So that just means that we're going to have 2 things inside the brackets and we're going to be expanding them out. So to get us started, we're going to look at some expansions of 1 plus x to the power of n. Now n is going to be starting from n equals 0, and we're going to be gradually increasing that power of n to see what happens. So starting at the beginning, if n was equal to 0, we would get 1 plus x to the power of 0. Anything to the power of 0 is always equal to 1. Then going on to the next one, if n is equal to 1, then we have 1 plus x to the power of 1, which is simply 1 plus x. If I want to expand 1 plus x squared using the shortcut method, 1 times 1 is 1. 1 times x is x, but we double that to be 2x, and then x times itself is x squared. If I want to expand 1 plus x cubed, what I can do is I can change that to be 1 plus x times a 1 plus x squared. Now we've already expanded out 1 plus x squared. That was 1 plus 2x plus x squared. Expanding that further, we want to multiply the 1 by each thing in the second bracket. 1 times 1 is 1. 1 times 2x is 2x. 1 times x squared is x squared. Now multiply the x by each thing in the second bracket. That would be x. X times 2x is 2x squared, and x times x squared is x cubed. There's a few like terms in there that we can collect up. We're going to leave the 1 at the beginning and we're going to increase in powers of x. So 2x plus another x is going to make 3x, a plus 3x. The x squared plus another 2x squared is going to make 4x squared, and then a positive x cubed on the end. Oops, that was a 3, sorry. Then to expand 1 further, we are going to multiply 1 plus x by 1 plus x cubed, because we already know what that is. So we have 1 plus x, and then our last expansion was 1 plus 3x plus 3x squared plus x cubed. Expanding out 1 times everything in the second bracket will be 1 plus 3x plus 3x squared plus x cubed. Then timesing everything through by x will be x plus 3x squared plus 3x cubed plus x to the 4. Now my increasing powers of x, starting with the 1 at the beginning. I have 3x plus, I should have some more x's in there. There it is, 3x plus x will make 4x. Then my x squareds will be 3x squared plus another 3x squared, which makes 6x squared. Then the x cubes, I have 1 plus 3 more makes 4x cubed, and an x to the power of 4 on the end. Now we could continue increasing our value of n and keep expanding more and more of these out. but it is a lengthy process and one that's easy to make mistakes, and we would prefer to find an easier method. Now, luckily, a guy called Blaise Pascal, when he studied these expansions, he saw a pattern. Now, let us see if we can find that same pattern. If we are to look at the coefficients of each of those expansions, the first expansion that we did, we just had a 1. So that was the coefficients. And we'll be looking at the coefficients here. Okay, in the second one, I had 1 plus x, so the coefficient of that x is also a 1. So that would be a 1 and a 1. In the third expansion, I have a 1, 2, and a 1. In the next expansion, it was 1, 3, 3, 1. In the final expansion I did, it was 1, 4, 6, 4, 1. Okay, now, can you see the same pattern that Blaise Pascal saw? What this triangle gives us is we know that the coefficient of the first and last term of every expansion is always a 1. And we can work out the next row in Pascal's triangle by adding the numbers directly above it. So for example, if I add 1 and 2, I get the number 3 that goes directly between it. Or if I added 3 plus 3, I get the 6 down here for the next row. And so we can add more rows and get as many different coefficients for however many power, whatever power we want, using Pascal's triangle. Now, one of the things that you will notice is that if my power was 0, I had 1 term. If I had a power of 1, I had 2 terms. If I had a power of 2, I had 3 terms. So whatever the power is, I always have 1 more term than that. That will help me with this next little statement down here. It says count the number of terms in each expansion. In general, if I'm expanding 1 plus x to the power of n, it is going to have 1 more than the power. So if the power is n, it's going to have n plus 1 terms. Now those terms are going to have increasing powers of x's. The first term is always 1, which is the same as x to the power of 0, which is equal to 1. And our x part of our expansion is always going to be increasing as we go along until we get to the same power. So this last one here was x to the power of 4, the same power as what my expansion, or from my question in my expansion up here. So if this is a power of 4, it means I'm expanding to a power of 4 there. So my last term is always going to have x to the power of n. Pascal's triangle and the addition principle. When the coefficients of these expansions are arranged in a table, the result is known as Pascal triangle. It was named after Blaise Pascal in 1623 to 1662. So on the next page, here is some rows already completed of Pascal's triangle. For a bit of practice, we're going to add a couple of extra rows here. So the 1 is always going to be on the outside of each row. To work out the next box, I will add 1 and 5, which will make 6. Then the next one, I'll do 5 and 10 to get 15. 10 plus 10 is 20. 10 plus 5 is 15, and 5 plus 1 is 6. Let's repeat that process for the next row. 1's on the outside. Adding 1 plus 6 from the row above, we get 7. 6 plus 15 is 21. 15 plus 20 is 35. 20 plus 15 is 35. 15 plus 6 is 21. And 6 plus 1 is 7. So in your first exercise, you're going to be asked to, very first question is going to ask you to complete Pascal's triangle for, I think it's about 10 rows. You'll want to do that on a separate piece of paper so that you can be using that throughout the questions that you do. We'll get something like this. There's my Pascal's triangle for 10 rows. So you'll need to keep that with you to help you complete the first exercise. Right, once you've got that triangle, we can use that to expand anything in that form, 1 plus x to some power. So let's see if we can predict 1 plus x to the power of 5. Okay, so let's start under here. 1 plus x to the power of 5. That means I'm going to use the 5th row down here, the one with the 5 in it. That is going to be the row that I use. It's actually the 6th row because the first one is my power of 0. So it's actually the 6th row, but the one with the 5 in it there is going to be the coefficients that I use to expand this out. So all I need to do is starting with a 1, that's going to be my first term. Then I'm going to plus. The 5 is going to be the coefficient of my second term, and it's going to have an x. And each term, the x power is going to increase. My next term, the coefficient is a 10, and that's now going to be an x squared. The next coefficient is 10 again, and it's going to be x cubed. Next coefficient is 5, that will be my x to the power of 4. And my last coefficient is 1, and that will be x to the power of 5. Now, we do know that because this was a power of 5, my last one should also be a power of 5, and it is. It's a bit of a check. Okay, let's go again. Let's see if we can expand out 1 plus x to the power of 6, which means I want this 7th row here, the one that has the 6 in the second position. And let's practice expanding that out. So 1 plus x to the power of 6, using those coefficients. 1 was the first coefficient. Then I'm going to have 6 for the second one, and I have an x. Then 15 for the third one will become x squared. 20 become x cubed. 15 x to the power of 4. 6 x to the power of 5. And finally 1 x to the power of 6. Okay, so hopefully you're finding that fairly straightforward, just using the coefficients from Pascal's triangle and our increasing powers of x. There are 3 basic properties of Pascal's triangle that we've covered mostly already, but here they are again. Each row starts and ends with a 1. You may have noticed that the rows are symmetrical, and every number in Pascal's triangle is the sum of the 2 numbers in line above it. All right, let's expand on this a little bit. We don't want to just expand things that are 1 plus x to some power. We want to put any little binomial, any little 2-term polynomial in our brackets and want to be able to expand it out. So what I'm going to be doing is I'm going to be changing the second term in each of our brackets. Now, to expand that out, we still need to use the coefficients from Pascal's triangle. So I know you can't see them anymore on the screen. We are wanting the 5th row, which is the one that is 1, 4, 6, 4, 1. So they're going to be my coefficients. So let's expand. The first coefficient was a 1. The second coefficient is a 4. And normally I would put an x there. But I don't just have a normal x in my question anymore. I have a 2x. So it becomes a 2x that I need to multiply with that 4. The next coefficient is a 6. So go plus 6. And then it's 2x squared that goes next to that. The next coefficient after that is a 4, and that will be 2x cubed. And the last coefficient is a 1, and that will be 2x to the power of 4. Now I need to simplify that a little bit. So the 1 can't be simplified anymore, but 4 times 2 is going to be 8x. Expand the brackets first for the next one. 2 squared is 4 times the 6 is 24x squared. Next one, 2 cubed is 8 times 4 is 32x cubed. And 2 to the power of 4 is 16x to the power of 4. That was fun, wasn't it? Let's try it again for b. So it's a power of 7 So we want the 8th row, which is 1, 7, 21, 35, 35, 21, 7, 1. They're our coefficients. So 1 plus 7 was the second coefficient, and the minus a, I need to take that minus sign. All the other ones we've done so far have been pluses. If there's a negative sign in there, it needs to come in as well. So that's where my x would normally be, the negative a. My next coefficient was a 21, and that will be negative a squared. Next coefficient was 35, negative a cubed. Next coefficient was 35 again, negative a to the 4. Next coefficient was 21, negative a to the 5. Next coefficient was 7, negative a to the 6. And the last coefficient was a 1, negative a to the 7. When I clean that up a bit, if I have an odd power in my brackets, then the minus sign is going to stay. So 7 times minus a is going to be minus 7a. But when I have an even power, like the next one too, if I square that negative a, it's going to become a positive again. So it'll be a positive 21a squared. The next one has an odd power, so that would be negative 35a cubed. And even power for the next one, so positive 35a to the power of 4. Next one's an odd power, so minus 21a to the 5. Even power, so plus 7a to the 6. And an odd power, so minus a to the power of 7. And that is it. One more of these to try, and this one has a fraction in it. So we're going to be using x over 2 for our increasing x's in the expansion. It's a power of 5, which means we want the 1, 5, 10, 10, 5, one line of Pascal's triangle. So first coefficient is 1. Next coefficient was 5, and x over 2 is going in there. My next coefficient is a 10, and that will be x over 2 squared. Next coefficient is a 10 again, x over 2 cubed. Next coefficient is a 5, x over 2 to the 4. And the last one's a coefficient of 1. It'll be x over 2 to the power of 5. When we tidy that up, the 5 will times to the top with the x. So 5 times x will become 5x over 2. Expand any powers out first though. So that would be x squared over 4, because 2 times 2 is 4, or 2 to the power of 2, sorry, is 4. And the 10 would sit out the front on the top of that fraction. Now the next one, I'm going to have the 10 out the front again. I do x cubed, and 2 cubed is 8. Next one, the 5 stays out the front. X to the power of 4 on the top, 2 to the power of 4, which is 16, on the bottom. And x to the power of 5 on the top, and 2 to the power of 5, which is 32 on the bottom. Now we have expanded, we've simplified, but there is actually a little bit more simplifying that can be done. For example, 10 and 4, we can divide by 2 to be a 5 and a 2. And also here, divide by 2, we get 5 there and 4 there. So we'll just rewrite that with the simplified fractions. All right, on to the next question. Okay, these ones are a little bit different. So question 2, it says by expanding the first few terms of 1 plus 0.03 to the power of 6, find an approximation for 1.03 to the power of 6. So, and we want that approximation to 4 decimal places. So this is the kind of thing that you'd normally just want to type into your calculator, but unfortunately we want to show that we can use binomial theorem to expand that out. So by taking the 1.03 and changing that to be a 1 plus 0.03, we have our binomial. We have two terms in the bracket there. So to expand that, it is a power of 6. We use the 7th row of Pascal's triangle, where the coefficients are 1. The second coefficient is a 6, and we would times that by 1 lot of 0.03, because that's where my x normally would be. My next coefficient was a 15, and so it'd be 0.03 squared. My next coefficient would be a 20, and that's 0.03 cubed. My next coefficient would be 15, and that's going to be 0.03 to the power of 4. And I actually don't need to expand the whole thing out because I only want 4 decimal places, and as you can imagine, when I square or cube or power of 4 the 0.03, those numbers are actually going to be getting quite small. I'm going to be getting down beyond my 4 decimal places. So once we've expanded what we think is enough, we go plus ... We know that there is more to that expansion, but it's going to be too small to be relevant to this question. Now we're going to use our calculator to simplify those numbers. We have 1 at the front. 6 times 0.03 is 0.18 plus 15 times 0.03 squared is 0.0135, and 20 times 0.03 cubed is 0.00054. So you can already see we're getting well close to our 4th decimal place there. We've got 3 zeros there before we even have 1 digit there that's affecting my 4th decimal place. And the next one is 0.0000. So there's my 4 decimal places, and they're all zeros. 1215. It's still important to include that term though, just in case that 1 might actually round something up that might go into the 4th decimal place. When you add all those numbers together, you get 1.1941 when it is rounded correct to 4 decimal places. Example 3. Expand 1 minus x to the power of 8 as far as the x squared term, and hence find the coefficient of the x squared in the expansion of this one down here. So the first part is to expand 1 minus x to the power of 8 as far as the x squared term. So let's start with that. 1 minus x to the power of 8. We don't want the full expansion, just to the x squared. So using the 9th row of Pascal's triangle, the first coefficient is 1, second coefficient is 8, and that we would need to put a negative x in our bracket for the first one. Then our next coefficient is 28, and it will be negative x squared. Now negative x squared becomes a positive x squared, so that actually is my x squared term. The next one would be my x cubed term, which I don't actually need. That's bigger than what I want. So I can stop there and go plus ... I don't want the rest of it. Let's simplify that. We get 1 minus 8x, and that will become a plus 28x squared plus ... Now that we have that, we want to continue our question. The second part of the question says we want to find from x plus 2, 1 minus x to the power of 8, we want to find the coefficient of the x squared. Now, this part here, we've already expanded out partially. So let's replace that with the expansion that we found. X plus 2, we'll leave that there. And my expansion was 1 minus 8x plus 28x squared plus my ... Now I'm looking for x squared terms. I don't care about the other ones, just the x squared ones. Now we don't want to expand everything out, we just want to look for the x squared terms. I could find an x squared term if I multiplied an x with another x like that. So when those ones get multiplied, I would get negative 8x squared. I could also get an x squared term if I multiplied the 2 with the 28x squared. That would give me a positive 56 x squared. In total, minus 8 plus 56 is 48 x squared. To write my answer, I was actually only interested in the coefficient. So I'm going to say, therefore, the coefficient of x squared is 48. Just want the coefficient for the answer. One more question here, example number 4. Find integers a and b such that 1 plus root 5 all to the power of 6 equals a plus b root 5. So we need to expand 1 plus root 5 to the power of 6. So 7th row of Pascal's triangle. The first coefficient is a 1. The second coefficient is a 6. Now the root 5 is going to be where my x would normally be. So that will be 6 root 5. My next coefficient is a 15, and then that would be root 5 squared. My next coefficient is a 20. That would be root 5 cubed. My next coefficient is a 15, and that is root 5 to the power of 4. My next coefficient is a 6, root 5 to the power of 5. And my last coefficient is a 1, which would be root 5 to the power of 6. Tidying it up, 1 plus 6 root 5. Those bits are already perfect. Root 5 squared becomes 5. So that is 15 times a normal 5. When I have root 5 cubed, I could take 2 of those. 2 of those would become 5, like in the last term. So 5. And I would also have one more root 5 on the end of that. For the next one, 15 out the front, I've got a power of 4 on that root 5. So 2 of them would become a 5, and then the other 2 would become another 5, or 5 squared. Next one, 6 out the front. I'm going to be able to bring 2 lots of root 5 out of there. So there's my 5 squared again, like I had in the last term. But there will be another root 5 as well. And finally, the root 5 to the power of 6, there would be 3 lots of 5 that I could get out of that. So in other words, 5 to the power of 3. Okay, that can still be tidied some more. We have 1 plus 6 root 5. 15 times 5 is 75. 20 times 5 is 100 root 5. 15 times 5 times 5 is 375. 6 times 5 squared is 150, and there's a root 5 with that. And 5 cubed is 125. Now there's only 2 types of terms here. There's normal numbers and there's root 5 terms. So 1 plus 75 plus 375 plus 125, they all collect up and we get 576. And then our root 5s, those can all be added together and we get 256 root 5. Now the whole goal here was that we were trying to find the a and the b up here. Now that we've expanded it, our answer is actually in that form. So the a is going to be equal to the 576, and the b, which is with the square root of 5, is going to be 256. And that's it. So you can now work on 15a.